Good afternoon, everyone, and thanks for tuning in. I will just say it was only half of my PhD thesis that was on W Aquilae, but this is going to be my fifth paper on the star, so it is fair to say that I have worked on it a lot. So, halide molecules around the S-type AGB star W Aquilae. First, a bit of a recap of what AGB stars are. So here is a little picture of the HR diagram. And when a star with low to intermediate mass, so less than about 8 or 10 solar masses, leaves the main sequence, so when it runs out of fuel in its core, first it will become a red giant star, and then it will ascend the second giant branch, or the asymptotic giant branch, and become an AGB star. AGB stars have an inert carbon or oxygen core, but they do still have some nucleosynthesis going on in shells around the core. So here's another illustration of stellar evolution, with this star being the AGB star. One of the main characteristics of AGB stars is that they eject a lot of matter. They lose mass quite rapidly. And the matter they eject forms molecules and dust in a circumstellar envelope, or stellar wind. We sometimes use these terms a bit interchangeably, around the star. So as the matter moves away from the star, it cools, dust starts to form, and then radiation pressure on this dust drives the wind. So we're very interested in how this dust is formed, so that we can understand, the whole mechanism of how the wind is driven. The sort of more low mass AGB stars can be divided into three categories. There's oxygen rich, S-type, and carbon rich. So there's a bit of an evolutionary progression here. So stars are oxygen rich when they first become AGB stars. And then through a process called thermal pulses, which are sort of more violent pulsations, not the sort of usual pulsations that take place on a period of like around a year. These happen much less frequently, but these thermal pulses dredge up material from inside the star. So, for example, carbon, also heavier elements. But as more carbon reaches the surface of the star becomes less oxygen rich, and eventually it will become carbon rich. And meanwhile, the S-type stars are an intermediate object. So they have carbon to oxygen ratios close to 1. And so they're not clearly dominated by oxygen-rich chemistry or carbon-rich chemistry. They're somewhere in between. And they're also a little bit rarer. They're a bit less studied. And W Aquilae, the star I'll mainly be focusing on, is such an S-type star. So as has maybe been suggested already, W Aquilae is the best studied S-type star, partly thanks to me. It's relatively close and has a moderately high mass loss rate, and both of these things make it easier to study. So its molecular emission lines are brighter, we can see them more easily. The high mass loss rate contributes to this because a higher mass loss rate generally means a higher wind density, which just means more molecules there for us to see. It also has a somewhat distant binary companion, which we know is an F9 star. And we also know that the projected separation is smaller than the real world separation. It doesn't have a very strong effect on the circumstellar envelope of this star, but it does have a little bit of an effect. It's probably responsible for a little bit of the spiral structure that we see. Also, W Aquilae is well studied because of its position in the sky. So it's close to the equator and in the south, which means that we can see it from ALMA. ALMA, of course, being, cutting edge ground-based telescope at the moment. And so being able to study it in detail using ALMA means that we just get a lot more information than if we couldn't look at it with ALMA. So a variety of circumstellar molecules have already been studied for W Aquilae. I've listed a few there, but what I'll be talking about right now are some other molecules which we've just seen for the first time towards an S-type AGB star. And these are the halide molecules. So I'll mainly talk about aluminium chloride AlCl, and aluminium fluoride, AlF, which we detected for the first time towards W Aquilae, so for the first time in any S-type AGB star, using the Atomium Large program, which I'll talk about a little bit more shortly. But first, why do we care about halides at all? Well, chlorine and fluorine, they're the actual halides. Chlorine is interesting because while it's not formed in AGB stars, it's mainly formed in supernovae, it can be used as an indicator of metallicity. So if we understand what the chlorine is doing around AGB stars, and then use that information to check how much there is, that can tell us something about the metallicity when we don't have other information on that. Fluorine, however, does form in AGB stars. The exact mechanisms are still a little bit unclear, but it seems to be that about half of the galactic fluorine has come from AGB stars, and that includes during the AGB phase. So fluorine, if it's being nucleosynthesized in AGB stars, it will be dredged up to the surface. And while, we're not sure exactly how rapidly it's being made, but if there's more fluorine, that can give us an indication of age. So perhaps if there's more, the AGB star has been an AGB star for a bit longer. And finally, a quick note on aluminium, which is not a halide, but it is thought to play a role in dust formation. So that's another interesting reason to study AlCl and AlF. I've also mentioned HCl and HF, the hydrogen halides, which are more difficult to observe just because they're light molecules with high frequencies, mostly in the terahertz range for their transitions. But they are thought to be the most abundant of the halide molecules, at least from sort of LTE chemical predictions suggest that we should be seeing a lot of HCl and HF. So that's just a little bit of background there. So Atomium is an ALMA large program. It was used to observe 17 AGB stars and red supergiant stars, of which, of course, W Aquilae was one. So with this program, we looked at 16 frequency windows in the 200 gigahertz frequency range using ALMA. And the results of Atomium represent the highest resolution observations of W Aquilae available so far. I'll just explain this overview plot that I've shown here because the observations were made using 3 different configurations of ALMA. And we refer to these as the compact array. So that's when ALMA was in the most compact configuration. And this gives us the lowest resolution data. And not all the frequency windows were observed in the compact array, which is why there are gaps here. Then there's the medium array, which, as the name suggests, is a medium configuration and also gives us medium resolution observations. And then there's the extended array, which is the most extended configuration of ALMA that we used for Atomium. And it also gives us the highest resolution observations of our sources. So in the process of reducing the ALMA observations, all 3 arrays have been combined, but sometimes it makes more sense to look at the observations of just one and not the other. And also combining the data is not completely straightforward, and it makes more sense to do that for sort of each individual line or set of lines that we're interested in, rather than for the whole thing. So I'll be showing some compact, extended, and combined observations in this presentation. So first, I will show you the CO line. So that's the brightest line in the compact array. And carbon monoxide is just a really ubiquitous molecule. It's a good tracer of density in the circumstellar envelope, and it's because of the very high binding energy of the carbon and oxygen, it tends to last to the most extended molecule that we can see in the CSE. So it gives us an idea of the overall structure of the circumstellar envelope. So these are what we call channel maps of W Aquilae as seen in CO, carbon monoxide. So this central panel is the systemic velocity of the star, and then we have the other slices at different velocities through the star. As you can see, there's a little bit of structure there. There's this red circle in the middle is the location of the star itself, and everything else is part of the circumstellar envelope. You can see what looks a little bit like absorptions, but that's actually due to resolved out flux, since ALMA, being an interferometer, acts as a spatial filter, and smooth large scale flux is resolved out. So even though this is the compact configuration where we hope to not resolve out flux, we do still resolve out some of the CO. But this is not important for our analysis, and I'm mainly showing you the CO so that you can compare these images with the halide molecules that I will show next. So looking at next, I'll show you, a zoomed in version of the central panel. That's what you see here on the left. So that's the background colors are still the CO in the compact configuration. And the tiny red dot in the center is the contours from ALCL. So the ALCL is shown zoomed in here. And this particular image shows, this is the same channel of CO, except on the right, I've used combined CO data because the compact is so low resolution, it would just be like, 3 pixels or something in this zoom. Whereas the ALCL data comes from combined, ALCL moment zero map. So that's when we add all the channels of ALCL, in this case, together. These are the contours resulting from that. And I use the combined data of the ALCL in this instance because it's a little bit smoother than the extended. We actually end up with a slightly lower resolution for the combined data to avoid too many noise effects. So that's what we see here. Basically, we have quite a large circumstellar envelope as traced by CO, which you can see on the left. And then the region of interest for ALCL is very small. And that's what I'll mainly be focusing on, though ALF, not shown here, is a little bit larger. But a little bit more about aluminium chloride. So here are the channel maps of aluminium chloride in the extended configuration now. So you can see the data is a bit noisy, but we do have sort of distinct clumps of emission. I'm not sure if it's going to be that visible over Zoom, but this circle indicates roughly the position of the star. Or sorry, it definitely indicates the position of the star. It is roughly that size. And this is the zeroth moment map, so the moment zero map, as I may have said before. And this is all the channel maps added together. So you can see the emission more clearly here because it's amplified by summing them. But what we see here is sort of a more of a amorphous structure, whereas in the individual channel maps, we can see individual clumps of emission. And really this just means that, the outflow is a bit clumpy. We're not seeing perfectly smooth and uniform outflow, which is not, a massive surprise. And when we add all the channels together, as we do here, you can see that it is also a little bit off center. So it's a little bit brighter on this side than on the other side, and not perfectly centered on the star. And this is, as I said, probably just because of clumpiness. So, the molecules don't leave the surface of the star in a perfect sphere, and then formation and things happen in a slightly clumpy structure. And as we saw on the previous slide, or 2 slides ago, the overall structure of the envelope is a little bit clumpy and structured. It's not perfectly smooth. So moving on now to aluminium fluoride, and here I don't have channel maps to show you because this extended emission that you can see in this zeroth moment map is actually quite faint and not very visible in the channel maps. You can only really see it when we add them all together to get the moment zero map. So the colors and the white contours are the ALF. I've put the same combined image, so from the previous slides of ALCL. I used the combined moment zero map for that instead of the extended one, just to avoid some of the sort of noise around the edges so that we can see the main point, which is that ALCL and ALF more or less form in the same location. And both of them are off center from the star in slightly different ways. So that red point in the center is the star. And these ellipses here are the resolutions of the ALF and ALCL emission. So what this tells us is, well, for some reason that is unclear, ALF preferentially for, there's more of it in the north in this, this diffuse emission is preferentially towards the north. And we also see the center emission is quite bright, and the outer emission is quite tenuous. So, okay, that tells us that ALF exists further out in the envelope than ALCL. It's still not very far compared with CO. So the CO channel maps had axes going to plus and minus 12 arc seconds, and here we're still at, 0.5-ish arc seconds from the center of the star. So it's still quite compact. But what we want to do now that we've got these observations, we've analyzed them a bit, what we want to find out is the abundances of both of these molecules. So the way we do that is we need to extract certain information from the ALMA observations that we can then reproduce with the radial transfer model. So for two reasons, I'm mainly using one-dimensional radial transfer modeling here. And those reasons are, one, we do need to include a lot of levels. These two molecules are both sensitive to the radiation field. The radiation from the central star will excite them up. So this is called infrared pumping. So it'll excite the molecules to a higher vibrational state, and then they'll cascade down to lower energy levels. And that part of the distribution of energy throughout the levels is important to include, because the vibrational levels for both molecules overlap closely with the frequencies or wavelengths of light being emitted by the star. So we know that it's important, and we know that we get different results if we don't include these levels. And the other issue is, even though the observations are quite clumpy, they're not clumpy in a sort of nice, neat, geometric way. So reproducing that in 3D at the moment is quite challenging. So we use 1D radial transfer modeling, and to take the sort of spatial information that we get from ALMA into account, what we do is we create a radial abundance profile, a radial azimuthally averaged profile of the data, which will allow us to find a radial abundance distribution with our model. So just going back to this image, we take the moment zero map and azimuthally average it, and then use that to compare with the 1D model, since the 1D model gives us a spherically symmetric result. So of course, this isn't going to be perfect, because as we can see here, this isn't spherically symmetric, but it's the best we can do at the moment. And it does give us an approximate abundance, and the inner abundances, which yes, are slightly off center, but aren't completely offset by a large amount from the star. So averaging them more or less works. So then we need to take the spectra from the ALMA data. So here I've collected all of the AL35CL spectra. So we do detect the 35 and 37 chlorine isotopologues, starting with 35 because that's the more abundant one. And we have actually quite a few up to V=2 vibrationally excited lines detected. I've included the V=3 lines just so that we can check for upper limits, make sure nothing strange is happening with the model. But the black lines are the data, the red lines are the observations. And then when we also take the radial profile of the data into account, we can, well, again here, compare the observations with the model. And then down here, I've plotted residuals, which are just defined as observation minus model with the same error bars that we have on the data up here, just to give an indication of how good the fit is at various points, with this dashed line representing a perfect fit, which of course we're never going to get. So I'll show you the actual numbers of abundances later, but this is the results of the modeling procedure. Then we do a similar thing for Al37Cl, except that we have fewer observations, fewer detections, I should say, and we just have the V equals 0 and V equals 1 lines detected. And because of the isotopolog, the frequencies and transition numbers that we see aren't exactly the same because they don't all fall within the frequency windows of the Atomium program. But this is the ALCL results. And then for ALF, it was a little bit trickier. And that offset, where there was more diffuse emission towards the north, is more or less responsible for this discrepancy. So even though it's averaged, we get a slightly different looking model versus observation. But overall, it's not a terrible fit, and it does tell us something about the abundance and sort of generally radially speaking, where or how much ALF there is at different distances from the star. So I'll get back to showing the numbers, but first I want to talk a little bit about other halide observations. So before I talked about ALCL and ALF, of course, I mentioned briefly HCl and HF, but two other halide molecules that are in general seen towards some other stars are the salts, NaCl and KCl. So previously, all of these 6 molecules have been studied only towards one star, and that's the carbon star CW Leo, which is the closest carbon star, which does make it very easy to observe. The results that the people who studied this carbon star found were actually very different for ALCL and ALF than they are for W Aquilae. They find both of these molecules are seen up to further distances from the star, so from the center outwards to further distances. The difference is especially clear for ALCL, but also for this CW Leo star, a lot of NaCl and KCl observations have been found and modeled, and etc., which have not been seen for W Aquilae. So transitions of these two molecules are covered in the Atomium data, but we do not detect these two molecules for W Aquilae. And then the hydrogen halides, well, these have been seen towards CW Leo as well, observed with Herschel Hi-Fi and PAX. So now, unfortunately, W Aquilae was observed with Hi-Fi, but not at the correct frequencies to see HCl or HF. Only CW Leo, I think, was observed in that much detail. But W Aquilae was observed by PAX. So here is the PAX spectrum of W Aquilae, plotted thanks to Pierre, and an image of Herschel. So we have this data. We know that it covers the wavelength ranges of some of the HCl and HF lines. So we decided to see if we could use this to find abundances or at least upper limits for these molecules. And we did. So using similar radiative transfer models, we found, so here the black lines are the PAX spectrum and the blue lines are the models. They're not, so these HCl lines are sort of detected, but the rest are used as upper limits. The only HF line which was detected was this one, which unfortunately is a very close blend with the water line. For the purposes of modeling, I subtracted the model water line from an earlier study, which I also did. That was my 2014 paper. So you can see in this plot, the gray line is the intensity of the water line from that model, and the blue line is the HF, and the dashed blue line is both of them added together. So you can see that does agree with the data, but unfortunately the 81 micron part of the W Aquilae spectrum is just very noisy, both for HCl and HF. I mean, they're near each other. So unfortunately, that wasn't very useful, but the 4 to 3 HF line is tentatively detected at around 61 micron. So to get these results, we of course didn't have spatial information. So PAX is not giving us spatially resolved information for W Aquilae, and it's also not spectrally resolved. But to account for the spatial side, we used chemical model results run by Midi van der Sande, which give us a prediction for the size of the emission region of both HCl and HF. So using these abundance distributions, we can just adjust the abundance up and down until it matches the data. So while we were looking at W Aquilae PAX data, I thought, well, a few other S stars were observed with PAX. Perhaps they also have HCl and HF. Why not check? So there were 2 other S stars observed with PAX. Pi Gru, we didn't find either of these molecules, but for Chi-Sig, we did. So I also did a quick model of Chi-Sig using a similar method with just the chemical models adjusted to account for the different mass loss rate and some of the different initial molecular abundances based on previous studies of this star. So Chi-Sig is actually the closest S-type AGB star. Unfortunately, it's in the north, so we can't observe it with ALMA, but we do have some Herschel data, as you can see here, and so we can find some abundances. And because it's closer, we have brighter HF lines, so they are detected, and also we can see something from the HCl. So we also got some nice Chi-Sig results while we were looking at W Aquilae. So now I'll show you the actual numbers. So this plot is the abundance distributions of the molecules I've been talking about for W Aquilae. The Alcl is found close to the star, and because of the clumpy nature, we actually see a slight increase in abundance a little bit further from the star, whereas for ALF, we see the opposite. So that outer tenuous emission is indeed a lower abundance than the inner region, which more or less makes sense. And then I've also plotted the abundance profile from the chemical models for HCl and for HF, which is shaded to represent that it's an upper limit. And in this table, I've just noted all the abundances for different stars that we know of for these 4 molecules. So as you can see, there's not that many AGB stars for which these have been observed. So that's something that would be interesting to change because, of course, one data point, one star, tells us about that star, but doesn't tell us anything about overall trends. So that would be something interesting to look into a bit deeper. But for the hydrogen halides, we did find similar abundances for W Aquilae and Chi-Sig, which isn't necessarily surprising. But of course, lacking any information about the aluminium halides for Chi-Sig, we can't really say, oh, well, okay, all S stars behave like this. We don't know yet. We can say that W Aquilae behaves quite differently to CW Leo, and that's most likely because one's an S-type star and one's a carbon star. So a lot of different chemical reactions are taking place. So some general interesting results that we found. So we saw the Alcl quite close to the star and not further out from the star. So it forms and is quickly destroyed. On the other hand, the ALF, as we saw, persists much further out. The reason for that is most likely, or at least partly, the very strong bond between Al and F compared with Al and Cl. So fluorine is its most electronegative element, and hence that bond is quite strong. So ALF is just less easily dissociated. We also found that the abundance of ALF in W Aquilae is higher than the abundance of fluorine that has been reported for the sun. So a higher fluorine abundance than solar is surprising until you think about that. Okay, I said at the start, fluorine is produced in AGB stars. We know that W Aquilae has undergone some thermal pulses, some dredge ups, because it's an S-type star, it has to have. So in that process, fluorine was probably dredged up to the surface. And that's why we have a higher abundance of ALF than just fluorine in the sun. So this supports the idea that AGB stars produce fluorine. The other interesting result, which is more an absence of results, is that we didn't see any aluminium oxide or aluminium hydroxide for W Aquilae. It wasn't detected at all. From the non-detections, we find these upper limits, which are quite low. This is the opposite of what like thermal equilibrium chemical models expect. They expect to see a lot of ALO and ALOH forming, and we don't quite know why this isn't the case yet. So W Aquilae being an S-type star, you could say maybe it doesn't have a huge amount of free oxygen, but it has enough that we have some water. So the abundance of water is something like 1 × 10⁻⁵. So that's a lot higher than these upper limits of aluminium oxide that we see. And we would actually expect ALO and ALOH to form from reactions between other AL molecules and water. And as I said, there is water, so this could theoretically be happening, but isn't. One possible reason for that is that the AL that would turn into ALO, or ALO quickly forms and then is destroyed by the process of dust production. So dust around S-type stars is not completely understood yet. Well, could say that for oxygen-rich stars as well, but for S-type stars, it's even less well understood. So this could definitely be part of the answer, but we don't fully know yet. So there's a lot left to explore. For example, we still have other observations of ALCl and ALF from the atomium sample for the oxygen-rich AGB stars, and I think some of the red supergiants as well. And some of those stars also do have detections of ALO, so it'd be very interesting to compare the distributions of those stars as W Aquilae and try and understand how and why the chemistry varies. So indeed, it could still be because of dust, but if we have different dust around the oxygen-rich stars, that could be a factor. It's also interesting if we can get time to observe HCl with ALMA. So I said most of the HCl and HF transitions are in the terahertz range, but actually HCl 1 to 0 is accessible from ALMA. It's in the 600 gigahertz range. And this would give us, well, spectrally resolved observations, which we don't have W Aquilae. But from what we've seen in Chi-Sig, should also show us some hyperfine structure. And most importantly for ALMA, it will give us spatially resolved observations, which will tell us if the chemical model predictions that I showed earlier actually match with, well, where the HCl really is around the star. So that would be an interesting line of inquiry. It's also possible to observe HCl with SOPHIA, which is the flying telescope, and then we can observe some more transitions. It would also be interesting to observe HF, but unfortunately there's currently no means of observing rotational lines of HF because they fall just outside of the windows that SOPHIA is capable of observing in, unfortunately. Nevertheless, overall, this is quite an interesting thing to study, and I think it's interesting to see how the different chemical processes work for different AGB stars, especially with regard to dust formation. So I'll leave it there. Thank you for listening, and does anyone have any questions?
Thank you very much, Taïssa. It was a very nice talk, very clear. If anyone has any questions, please mention it in the chat and I will call out your name. As usually, I try to give preference to the younger students. Dave, please.
Yes, hi Taïssa. Thanks for this presentation. One of your conclusions was that actually you observe a higher ALF fraction than solar fluorine gives you. And you concluded that the fluorine must have been produced within the AGB star and dredged up to the surface. However, I wonder, since I recently read a paper by Carlos Abia, who said that the only observationally confirmed source of fluorine 19, which is the only stable isotope of fluorine, is our carbon-rich AGB stars. Now, W Aquilae is a S-type AGB star, which is prior to the evolution or formation of carbon stars. So
I've also read that paper and the earlier papers that it refers to, which, I mean, that paper is building on earlier observations, finding an excess of fluorine towards a variety of evolved stars. They just find more excess fluorine towards carbon stars, indeed, than towards M-type stars. The nucleosynthesis processes happening in these stars shouldn't change very much across the AGB. I mean, you know, the same nucleosynthesis happens and is just dredged up gradually. So there's no reason to think that fluorine suddenly starts forming once a star becomes carbon rich. And that Abia paper, I believe they were reanalyzing older data, is that right? Or anyway, they found that the fluorine excess was less than previously reported.
Exactly.
Yeah, but that doesn't mean that there isn't an excess. And yeah, the exact mechanism, as I said, is still in dispute. But the fact that some fluorine comes from AGB stars, I think, is not in dispute. And the fact that they see more in carbon-rich stars makes sense because they've undergone more dredge-up events, more thermal pulses. Does that answer your question?
Kind of, yes. I mean, because if I reformulate to say the nuclear processes, which is essentially hydrogen and helium burning itself, they don't change the fluorine so much, but the dredge up kind of.
Well, the dredge up is bringing the results of nucleosynthesis up to the surface. There's also why S stars are called S stars, because S process elements made during this low neutron capture process are dredged up to the surface.
Yes, I agree, but they also bring previously initial products up, no?
Sorry?
They also dredge up elements that have been not produced by the AGB star.
Well, sure, but they should be roughly evenly distributed. So, for example, chlorine is not produced in AGB stars, but the amount of chlorine dredged up shouldn't change the concentration of chlorine because it was already there. Some of it was already on the surface originally.
It's just mixing, I understand, yeah.
Yeah.
Okay, thanks. Oh, maybe if I may, another
Sure.
question. So you mentioned like the salty species, sodium chloride and potassium chloride. But what about potassium fluoride and sodium fluoride? Is there any indications that they might be present?
So I don't think either of those have been detected for any AGB stars, not even CW Leo. And I think the reason is probably because both, well, fluorine is the least abundant of like the lightish elements up to, I think it was up to 35 or something like that. Fluorine is the least abundant. So there's that problem, and potassium is also not very abundant. Sodium is slightly more abundant than potassium. So forming that is a little challenging, and the abundances we would see are probably quite low. I haven't looked at what frequencies those molecules might be visible at, so I can't guarantee that it's not one of our unidentified lines, but it's not something that's ever been seen in an AGB star yet.
Okay, thank you.
Okay, anyone else have a question? It seems to be all have been crystal clear. So if no other question, I would like to thank Taïssa again for this nice talk. And we will see each other again next week on Friday afternoon. Thank you very much, everyone.